Hello, everyone. Thank you for coming to this talk. My name is Gene, and I have my colleague here, Chen Hao, and we're excited to talk about the variant data type in Spark and Databricks. And we'll be talking about how the variant data type can make semi-structured data fast and simple. So here's a brief outline of what I'll be talking about today. First, I'll go through some of the motivation of why we're working on the variant data type. Then I'll briefly introduce the overview of the variant data type and how you can easily use the variant data type in your queries. And then Chen Hao will come and give a deep dive on the variant binary format. And he'll give a lot of the details and special features for this format. And lastly, we will end up with some of the cool performance numbers that we have. So the main driving factor for working on variant is how do we deal with semi-structured data in the lakehouse? So semi-structured data is data that has some structure, is partially structured, but it doesn't fully adhere to the relational table model. So each record has some structure and schema, but it doesn't necessarily have to be the same across rows, or it may change over time, or the users may not even know what the structure is. So there's some schema there, but it's not always well-defined. And for example, JSON is a very popular format for semi-structured data, and the reason it's so popular is because it's so flexible and it's available in all the languages. So it's very easy to use, very easy to put data in and take data out because it's so flexible. So ultimately, the question is how do we store and process semi-structured data, flexible semi-structured data, in the lakehouse? So you might be thinking, like, why is this a hard problem? Like, we already know how to do this. This has already been solved. Well, let's talk about some of these options. So one option we have is schema inference. What we can do on ingestion is take the semi-structured data, read it, and then infer a schema from that semi-structured data. So we can, and since each of the records have a schema, we can determine the schema of structs and types and arrays and whatever is in the data, and we can develop the schema, and then we can create tables with that schema. And then when we ingest the data, we can parse the semi-structured data and fit them into these tables. And then when a read query comes in, it will just have to read the table like any other table, since it's already created with a schema. And the performance is actually identical to any table with that schema because the semi-structured data is no longer semi-structured anymore. It's fully structured now. However, there are some challenges to this approach. The main challenge is that the schema inference that we have to do has to fit all the data that it sees. So what happens is we could potentially produce a schema that is very large because it needs to fit all the data it has seen. This could create a very wide schema, a very large schema, and a very sparse schema because a particular record might only take a fraction of the schema in the table. So this can negatively impact performance, and also it's hard to deal with a table with thousands or 10,000s of columns. Like, users can't use that easily. Also, schema inference is strict. So what that means is if any new data comes in, it has to fit that table schema. That's just how schemas work in databases. So if there's some mismatch there, it's going to have to error out, and you're going to have to do something manual to try to fix that. Also, accessing missing records or fields in the schema just won't work because that's not how databases work. You need a very strict schema to access your data. So ultimately, this approach works, but it's way too strict. Semi-structured data is supposed to be flexible, but we're trying to force it to be very strict. So there's some downsides here. Well, there's another alternative we have. We can store semi-structured data as a string. And here, on ingestion, we don't care anything about the schema. We just stuff it into a string, and we can save it into the table however we want, because there's no schema inference, there's no schema enforcement on ingestion. So this is very easy and very flexible. And when you do the read queries on that data, during the query execution, we'll have to parse that JSON string and sort of pull out the data we want in order for the rest of the query to execute. So in this approach, it's very flexible. We can take any data in, and we'll just deal with the schema later. However, there's challenges with this approach as well. And the main challenge is that this can be very slow. Parsing JSON, parsing semi-structured data is very slow. And since typically in a lot of scenarios, we write the data once and then read many times. So what we're essentially doing is passing off all this expensive parsing to every single query for forever. So it's a lot of, ultimately this approach is too slow. It's very flexible, but too slow. So ultimately, we have these two choices when dealing with semi-structured data. You can choose the schema inference approach. That's way too strict for semi-structured data. Or you can choose the string approach, which is too slow for semi-structured data. So we took a look at these two choices, and we didn't like these choices. None of these choices are great. So we decided to work on variant. Variant is an open, flexible, performant type for semi-structured data. And with this new work, we don't have to deal with those two choices, two suboptimal choices anymore. So variant has three main components or features to it. One, it's open. All of our code for variant is in open source. It's all already have been committed to Spark and Delta. There's a new type in both of those systems. There are new variant expressions, and we also have a library that deals with the variant binary encoding format. It's also very flexible. We can put any type of semi-structured data into this type. We don't need schema when we ingest. There's no schema involved when we ingest the data. And we take a schema on read approach when reading the variant data. Now, in contrast to the string approach, variant data is much faster. It's very fast. And that's because we have a new variant binary format that we use to encode the data in. We don't have to parse strings anymore. And with this binary format, it's an offset-based binary format, so it greatly speeds up the navigation. So a little bit more details on the open sourcing. Like I mentioned before, we've open sourced all of our code. Everything has been committed and merged to Spark 4.0 and Delta 4.0. And for released versions, I think Spark 4.0 and Delta 4.0 preview versions have been released recently, maybe in the past few weeks. So you can check it out already today in those versions. We also have an open source library that deals with the binary format and it can encode and decode. And it makes it much easier for other projects to easily support the variant data type. And we're actually looking forward to adding support to this variant data type in other projects in the future. As I mentioned before, we also added new variant expressions to Spark. And here are some of the main ones. The first one is parse JSON. This is the main expression to essentially create a variant object. Essentially, it takes in a JSON string and produces a variant. ToJSON is the opposite direction. It takes a variant and produces the JSON string. We have variant get, which is the main way to essentially extract a piece of data from the variant. So you can provide a path and a type that you want it, and then it'll return you that piece of data. Cast has been updated to support casting to and from variant. We have schema of variant, which can detect a particular schema of a variant. And we also have variant explode, which will essentially unnest a variant object or variant array. And so here are some brief examples of how you can use variant easily in your queries. The first example, you can easily create a table of a type variant like any other type that you have in a database. In the second example, we have parse JSON, where we take a JSON string and produce a variant expression from that JSON string, and you can use it however you want after that in the query. In the third example is an example of how we extract a piece of data or extract a path from that variant. So here we have, we're extracting, say, path ABC from the variant, and we want it as an integer. So with this expression, we can easily take out that path as an integer for the rest of the query to use. And in the last example, we can use variant explode to easily see the keys and values of a particular variant object. So these are just a few examples of how we can use variant in our queries. So next I'll invite Chen Hao up to talk about a lot of the gory details about the variant format.
Okay, good afternoon, everyone. Today I will be discussing the variant binary format, a method used to represent semi-structured data efficiently. We use an open binary encoding instead of plain text to represent semi-structured data. The key feature of this encoding is that it uses offsets to enable a faster path navigation. Each variant entity contains two binary blobs. The first blob, called metadata, holds a dictionary of keys, and the second blob, called value, contains the actual variant data and its structure, which refers back to a dictionary in the metadata. The on-disk and the in-memory formats are identical, ensuring that the binary blobs can be easily accessed and manipulated without the need for complex transformations. The binary formats also allows for more compact data representation, which is crucial for optimizing storage and transmission, as well as reducing memory footprint. According to our internal experiments, the binary encoding usually has a smaller size than the original string representation. A typical size reduction rate is about 50%. We will explain the binary format in more details with this simplified example of a variant object. So for the metadata blob, it contains a header and a dictionary of keys. The dictionary size indicates the number of keys. The key offset values point to locations of the respective keys in the key data section. On a high level, this metadata can be considered a list of distinct strings that can be accessed by index in constant time. The header contains certain information on how the reader should interpret the following bytes. For example, we embed the version ID in the header of the metadata. This allows for future extensions and upgrades to the binary format while maintaining backward compatibility. For the value blob, it also has a header followed by the number of fields. It then contains a list of field ID values, which refer to the dictionary keys. We use these ID values as indices to get the field names from the metadata. It then contains a list of field offsets and the actual field value data. The offsets point to locations of the corresponding field value. The offset list is parallel to the ID list, meaning that the two elements at the same index belong to the same field. For example, both field ID 1 and field offset 1 belong to the field 1. The fields are lexicographically ordered by the field names. This is to enable a binary search over the fields and enhance path navigation, and we will explain it in a later section. The key advantage of this design is that it avoids storing duplicated field names multiple times in the variant value. Instead, each distinct key only needs to be stored once in the metadata, and multiple ID values can point to the same key. This is particularly beneficial when dealing with arrays of homogeneous objects and other situations with a lot of duplicated keys. Additionally, this separation can offer a better storage compression when stored in physical formats like Parquet due to dictionary encoding. For example, suppose we convert this JSON record into variant. For simplicity, we are using a JSON-like notation to describe the resulting variant value and the metadata. Under the hood, they are still binary encoded. These red numbers represent the field ID values, with 0 pointing to key 1 and 1 pointing to key 2. As it shows, the keys appear multiple times in the original JSON representation, but only once in the resulting variant. Overall, this structure offers a compact data representation and efficient field access. We will demonstrate an example of path navigation to show how the variant binary format helps. When we want to extract a certain field from a JSON string, we have to perform a sequential and linear search over all the fields in the JSON object, matching the field names one by one. Suppose we want the value of field 100. we have to check all the 99 fields before it. And due to the nature of the JSON grammar, it is not possible to only look at field names. Instead, we have to parse all the JSON tokens until we meet the desired field. All these efforts will eventually be useless. The sequential search approach is inherently slow because the expected search time is proportional to the size of the JSON text. If a query accesses multiple fields in a single JSON record, it may need to scan through the JSON text over and over. Additionally, the complexity of the JSON parser introduces a large constant factor to the algorithm, further slowing down the operation. This inefficiency becomes particularly problematic when the JSON data gets large, leading to increased computational overhead. In contrast, the process of extracting a certain field from the variant binary format is much more simplified. Instead of sequential search, we perform a binary search over the fields to locate the desired field. In this example, suppose we also want to find field 100. We cut into the middle of the field list and compare field 50 against field 100. 100 is greater, so we continue the search in the right part of the list and check field 75, and so on. Unlike JSON, the efficiency of this search process is not affected by the field value data. This method significantly reduces the search time and scales well when the record gets large, because the binary search has a logarithmic time complexity. The search requires no more than tens of comparisons for any practical data. Once we have located the desired field, we can directly jump to the position of its offset value. And then, based on this offset value, we can directly jump to its actual value data. In conclusion, this approach minimizes the time and computational resources required to access specific fields. Let's welcome Jim back to talk about the performance result of variant. Thank you.
Yeah, thanks, Chen Hao. Yeah, I mean, this is just a really cool format that we've been working on, and thanks for all those details. So next, I'll be talking about some of the performance benefits that we've been seeing with variant. The main benchmarks I'll talk about today are the two here I listed here, and we've named them TPC-DS JSON, TPCH nested. So TPC-DS JSON is essentially taking the original TPC-DS dataset, but converting it into a JSON or variant dataset. And the way we did that is we take every single row of each TPC-DS table, and we convert each row as a flat JSON record for the JSON table, and then convert that into a variant for the variant record. So that's for the first benchmark. The second benchmark that we worked on was actually using the TPCH base original data set, but instead of having it flat JSON records, we actually denormalized the data. So we used joins and arrays and structs and things like that in order to denormalize the data and create nested JSON records. And so with the nested JSON records, we created a table of tables of JSON records or tables of variant records. So you can, these are the two benchmarks that we looked at. So here is a summary of the performance gains we get with variant. Here we're comparing the completion time, the relative completion times of the full benchmarks. And so the blue is the JSON represented as a string, and the red is the JSON represented as a variant. And this is all relative to the JSON as a string runtime. So, and these are times, so shorter lines are better. And so as you can see, the red bars are much, much shorter than the blue bars, which means variant is much, much faster than the string approach. For TPC-DS JSON, it's about 8 times faster. And for TPCH nested, it's about 20 times faster. So this really highlights how, by using the variant binary format, we can greatly speed up the processing of the data, parsing of the data, and the query performance. Next, I want to talk about essentially a sneak peek in what we're doing next. So everything I talked about before has already been committed to all the projects, but this is something we're actively working on now, and that's variant shredding. So variant shredding is a concept where we take certain pieces, certain paths from the variant binary and store them in a separate column in the file. And while doing so, we actually remove that piece of data from the variant, the binary, and then put it in the separate file, separate column. By doing this, we can further improve the performance. And the reason is because, one, we can use less I/O to retrieve the relevant data that we want. There's also less CPU involved by not having to decode as much or parse as much. And we can even use min-max stats to enable data skipping. Ultimately, all this work and this effort is to improve the performance so that it's nearly equivalent to a fully structured table and fully structured data. So one example, I'll show you an example of what it might look like. Here, let's say we have a file of variant values, and today, without shredding, we have 3 variant binary blobs sitting in the file. And we've also color-coded some of the pieces of data. You can think of like the purple as all being the same path in each binary. The yellow is all the same path, and the blue is all the same path. So they're all in the binary today. With shredding, it looks more like this, where we actually have separate columns for each of these yellow and blue and purple pieces of data, and they're also fully typed in that column. And they're actually removed from the binary, so the binary is actually smaller in this case. So this is what it looks like on disk with the shredding involved. Now, how does this work in a query? I'll show you a small example of how this really helps. So with shredding, without shredding, the data looks like I've shown up here. And whenever, let's say the query wants the yellow piece of data. So the query, whatever query we wrote, wants the yellow data. So how do we process that today? Today, we have to read all the variant values from the file. And now we read in all the full binaries. And once we have the full binary pieces of data, we then have to parse the binary data to extract out the yellow piece of data to give to the rest of the engine and for the query to execute. So this is what's there today without shredding. With shredding, the files look like this now. And the query still wants the yellow piece of data. So in order to get that data from the files, the query only needs to read that single column already separated out in the right type and then give it up to the query. So what this really does is it eliminates all the extra I/O required. We only need to read the yellow data and nothing else, and then we don't have to parse or decode anything in order to give it to the rest of the query engine, since it's already in the correct type. So this really highlights how shredding the data for variant can greatly improve the performance and actually match the performance of fully structured relational data. So yeah, I just lastly want to finish up by saying that with this new data type, it's open, so everything is fully open sourced. Everything is, well, up till now has already been committed into open source in Spark and Delta, and more in the future. It's flexible, so we don't need schema when we do the ingestion, and we can ingest any type of semi-structured data. And it's performant because of the new binary format. We can navigate very quickly, and with shredding in the future, get close to the schema'd and structured performance. That's the end of our talk. Thank you very much. And